Welcome. We're going to go through our third example, our third type, I should say, that would be represented on your third Just the Basics JTB quiz. And a real quick intro to this one, because on your list of derivative rules, I never gave you the rule for e to the. So the derivative of e to the x, let's switch pens here, is wonderfully just e to the x. And therefore the derivative of e to the 2x is, and I will fool everybody in class on this because everybody will just say it's e to the 2x. It is e to the 2x. However, there's an inside function here we have to multiply by, so we get 2 e to the 2x. This is a chain rule. So if I had something like e to the 5x squared minus 3x, the derivative of that is e to the 5x squared minus 3x times the inside derivative, 10x minus 3. Okay, so hopefully that suffices based on previous discussions of chain rule. But finding the derivative of e to the x is our favorite. However, oftentimes we forget the little heartbreaker and we don't treat the baby function. Okay, so with that, this is going to be a much easier problem than our type 2 as far as the algebra goes. The one thing that might be a little bit tougher is just analyzing what the graph looks like. So first we're going to find the domain. I can multiply any number I want times -5, and I can take e to positives, negatives, 0. It doesn't matter. I can multiply any two numbers I want. Therefore, my domain is all real numbers, or negative infinity to infinity. And the only way this function is going to be 0 is if x equals 0. E to a positive is positive. E to a negative is still positive. And e to the 0th, of course, is 1. So the only 0 we get is at 0. And now we're going to go back and we're going to talk about our big X test to see what eventually is happening. And as I put a big value for X in here, what's not even a real big value, just 100, I get -500 times e to the 300th. Well, that's 2.7 to the 300th. That is trillions and gazillions and Brazilians, and it's just huge, huge, huge. So I get a big negative number times a crazy big negative number. This thing's going down eventually. Now let's put a big negative in here. Like, let's say a -100. So I get 500. I get a positive number here. And if I put in negative here, e to the negative, let's say I put in -100, e to the -300 is still a positive number. We're going to get positives. But e to the negative 300 is like 0.0000000. I mean, it's crazy close to 0. And while 500 is big, it's not big enough to get us away from 0. So here's what I'm suggesting is going to happen. Eventually, with a negative x, I'm going to get positive times positive. We're going to be positive, but we're going to get sucked in closer and closer to 0. Okay, with that, let's start talking about derivatives. So I'm going to find -5x e to the 3x's derivative. So that is equal to, this is a product rule, first function times second function. I want the plain old first function times the derivative of the second function. Well, e to the derivative is e to the. However, we have this inside function. The derivative of 3x, or the baby function, is 3. So that's first times the derivative of the second plus derivative of first, that's a breeze, -5 times the just plain second. And on these e to the's, we're going to get some common factors for sure. I get -15, x e to the 3x plus -5 e to the 3x. So I can factor out a -5 and an e to the 3x, and I'm just left with 3. The x is still here, factored out the negative, plus 1. So that is it. Much easier than the type 2 JTB problem we were looking at. So my first derivative is -5 e to the 3x times 3x plus 1. And if we have it nice and factored, the next thing we do with the derivative is we set it equal to 0 typically. And if we have it factored this nicely, pretty clear that it's 0 at negative 1/3. So at negative 1/3, that is the only place the second derivative is 0, and it's the only place the graph levels off anywhere. Well, I'm going to go back to this 0 point and put 0 into my derivative. If I put 0 in here, I get negative 5. E to the 0th is 1, so far negative 5 times 3 times 0 plus 1 times 1, negative 5 times 1. That tells me that my slope when x equals 0, so here's what we found. F prime of 0 is negative 5. That tells me my slope here is pretty steep, negative 5. Pretty steep here. Looks something like this. I'm going to flatten it out just for purposes of viewing here. And then it comes up and it must level off right here. And then it comes down and it's getting sucked into 0 eventually. And on this side, we know it's going to continue down. Now, does it level off? Does it get steeper? Does it wiggle around? That's a future study. We may be able to determine what is happening just by really giving a lot of thought to this, but I'm going to continue on from now. Therefore, we have a maximum at x equals negative 1/3, and if we wanted to know what the y value was, we could put in negative 1/3 and negative 1/3. It actually wouldn't be too bad, but we're just going to leave it at that. And if that's the maximum, and I know this thing's going down forever, end model behavior, the function is increasing until negative 1/3 and decreasing after. And there is no minimum. So it is increasing from negative infinity until I get to negative 1/3, and it is decreasing from negative 1/3 forevermore. How do we know it doesn't come down here and eventually level off and come back? Because it can't level off again. The slope's 0 only once, so that can't happen. Okay, we are set for the second derivative. So I'm ready to find the derivative of negative 5 e to the 3x times 3x plus 1. Once again, product rule. I want the plain old first function, negative 5 e to the 3x times the derivative of the second, 3, plus the derivative of the first, negative 5 survives, e to the 3x, but times the derivative of 3x times 3, derivative of first times the just plain second. Now we got some cleaning up to do here. Let's see. I get negative 15 e to the 3x. I get minus 15 e to the 3x. Well, that's convenient. Times 3x plus 1. Let's factor. I can factor a negative 15 out of both terms. I can factor an e to the 3x out of both terms. I'm left with just a 1. I factored out the negative plus. I factored out the 15 e to the 3x. I did not factor out the 3x plus 1. So my second derivative I'm claiming is negative 15 e to the 3x times 3x plus 2. Negative 15 e to the 3x times 3x plus 2. And if we get this in nice, clean, factored form, easy to tell. The only way we can get 0 is if 3x plus 2 equals 0. 3x plus 2 equals 0 when x equals negative 2/3. So we have an inflection point at x equals negative 2/3. So at negative 2/3 over here, that is where we go from this cupping up till we start cupping down. Try to kind of accentuate that. And therefore we have a function. And notice, earlier I asked, well, how do we know it doesn't do this? Well, it can't do that because the cupping's changed then. So it must just, as it comes out this side, it must just keep getting steeper and steeper and steeper. I think we probably figured that was the case because remember when e gets positive, this gets bigger, and this gets crazy bigger. So with the -5, we're going to, as x increases, we're going to go down steeper and steeper. That's confirmed with our knowing our only inflection point is at -2/3. So we are cupping down, or cupping up, excuse me, followed by cupping down forevermore. We're concave up from -infinity until I get over to -2/3, and we're concave down from -2/3 forevermore. -2/3 to infinity. So algebraically easier, just graphing. Once again, we're back to what I referred to as our big X test, which also could be a discussion of what's the limit as x approaches infinity, what's the limit as x approaches -infinity. We're getting sucked in here, and we're just running out of control now. So that would be one that I would expect that we'd be in pretty good shape. You want practice on this? Here's what you can do. Change this value, change this value. This value could be 1, 2, 3. It could be -6. This could be any value we want here. And I would put an integer here. Otherwise, it's going to fit this form. Okay, good luck. Let me know if I can help.